In this video, we're going to talk about looking at the characteristics of distributions. We have our vision data, and we have selected cases where the refractive status at the end of the study equals the myopic status at each visit. So we're looking at myopes when they were myopic and emmetropes when they're emmetropic. Also, we have looked at the last visit that they were in the study. So study year equals last study year. Further, we have split the file. Notice there's a split file and a split into files. We want the split file. Split into files would let us make 3 separate SPSS databases based on how we split them, say refractive status. But here we have a split file. We're going to do it on refractive status. That way when we do our little statistics here, we will do it once for myopia, emmetropia, and hyperopia. Alright, so let's first start by, and notice regardless of whether you're in the database or the output screen, you can get to analyze. So it doesn't matter really where you start it up. But let's look at descriptives, frequencies. For this time, let's look at spherical equivalence again. And for statistics, we want to know about quartiles. We want to know about the mean, median. We could do the mode, but who cares? That's not a very popular one. We can look at standard deviation. We can look at variance. We could look at min and max, but it's not all that necessary because we're going to get the distribution. But we'll do that. No, actually, I'm not going to do that. And skewness and kurtosis are 2 very important variables. Skewness tells us if the distribution is not symmetrical and which way does it go. Kurtosis refers to how peaked it is. And so let's look at these. And another thing we want to do is we want to look at our charts. We want to look at a histogram. Normally I don't bother showing the normal curve on the histogram, but here we're going to be interested in looking at all the measures that are normal so we can see what an imposed normal curve should look like. Okay, and let's see what that does. All right, so we get statistics, and 1 is myopia, 2 is emmetropia, and 3 is hyperopia. Let's fix that so in the future we won't have to remember what everything is. Under ref status, a 1 is myopia. Notice this is in the values labeled. A 2 is emmetrope. Number 3, and the way I do this, I hit the 3, I press tab, and I type hyperope, and I hit enter. So it's tab enter, and then it goes back to the original. This puts this in this column under values, and now it will label our graph when we go out. If you don't get those labels, check and make sure that value labels are checked under view. All right, let's just run it again since we're here. Frequencies. Notice it remembers everything that we put in before. You can do it again, just add it. And here we go, myopia. I should have made that myope, I guess, but anyway. So here we get our mean of -2, median minus 1.9, that's the 50th percentile, standard deviation, the variance, and so forth. Skewness. What is skewness? Minus 1.367. The myopes are a little skewed to the left. That means that there are some big myopes in our group. Notice skewness for emetropia is not very big, 0. So no skewness at all is 0. A normal distribution has a skewness of 0. And here, notice our skewness is really skewed at 3.499, but that's skewed to the right. So we have quite a few really high hyperopes. We get the percentiles. Okay, kurtosis is kind of an issue too, and I have to, okay. So then what we do is we get myopia, we get all the values. Now, here's an important thing. So there was one person that had a minus that was -7. There was one person that was a -6. The percent of the total is 0.3. Valid percent is 0.3. Now, what does valid and percent mean? If we come to the bottom of this thing, which seems to go on forever and ever. Whoops. I guess I passed it. Maybe I didn't have any missing data. That's odd. Must not have any missing data. If it's missing, if there's data missing, then this percentage would be based on the total. And then the right-hand column is the cumulative percentage. And you can go into this little pivot table, which also looks at stuff. You can manipulate it a little bit more there, but we're not going to do that. So notice 0.3, 0.3 plus 0.3 is 0.6. 0.3 plus 1.7, well, that's a rounding thing going on there, but anyway, it's a cumulative distribution. All right, let's look at our charts. Whoa, that's the, remember it had a negative skew? That's what a negative skew looks like. This is what a 0 skew looks like. This is what a positive skew looks like. Now those numbers, 12 and -8, those are not that far off of what would be perfectly reasonable. When you're first cleaning your data, you look for numbers that are way out of bounds up here. And that will help you. So that's our skewness. Now let's ask the question, do our distributions significantly differ from normal? And there's a non-parametric test. We're going to go to legacy. I prefer the legacy ones because you have to do more stuff to use the other ones, and this is just quicker. So legacy and a one-sample Kolmogorov-Smirnov test. And we're just going to look at spherical equivalence. And our options, we could put in descriptives and quartiles, which would be just like we did above. And this missing values, if you don't exclude test by test, like we have a variable called toricity in ours, which is only measured on a few. If we had chosen exclude cases listwise, even though we have lots of spherical equivalents, it would only give us spherical equivalents for those that we had toricity. So exclude cases test by test, and we're going to look for the test distribution normal. I'm going to say OK. And so here's our mean, standard deviation, the percentiles. Those means should match above. The median, the 50th percentile should match what we found above. And let's come down here and look, myopia. We rejected the null hypothesis that that our distribution was normal. So the null hypothesis is normal, a normal distribution, we reject that. For emmetropes, the p-value is 0.2. And remember 0.05, we want something less than 0.05 to reject, or 0.1 maybe even in this case to be really safe. It's 0.2, so we do not reject the null hypothesis for emmetrope, which is what it looked like in our graph above. And for hyperope, it is a rejectable thing. It doesn't match our normal data. Let's look at another way of measuring our normality, QQ plot. That's under Descriptive Qq Plots. And we're going to look at our spherical equivalence. And we're going to look at a normal distribution. We're not going to do any transformations. And we're just going to say, okay. Now, what does this look like? We get the mean and standard deviations. That's what location and scale for the normal distribution are. And here is our QQ plot for a normal distribution for myopia. Now, if this were, well, let's look and see what a normal distribution is supposed to look like. This is our normal, this is our emmetropes. We want all the dots to fall on a straight line. The tails might be a little thick or a little thicker than we would like. What this graph is it looks at the frequency of each of these points, and down here, which are the observed spherical equivalents. And see, here's 0, here's plus and minus 25. Notice that the emmetropes do not have 0 as their mean. It's a little towards hyperopia. And if we look at the expected value, that's taking a normal distribution and looking at the cumulative normal distribution, how many, given the frequency of each point down here, the cumulative distribution, what is the cumulative frequency in the normal distribution that you would expect? And so if we look at the myopes, we're finding a lot more negatives than we would expect, and a lot fewer positives than we would expect in a normal distribution. That's why we get the skew. If we look at the hyperopes, it goes the other way because it's a right-handed skew. So this isn't falling on the axis, the straight line. This line through here is the line of identity. They would be the same, 0, 0. And everybody's up pretty high there. So when you look and evaluate your data for normality, we have these three different ways. We have the QQ plot, we have the Kolmogorov-Smirnov test, and we have just looking at it in the frequency distributions, the histogram within the